Okay. We're going to talk about inducing an electric current, and if you are one of my kids, then you definitely know this. If you're not one of my kids, you might not know this. I'm a huge fan of Lorde, so I'm making a reference here. We will never be coils, parentheses coils, to her hit song Royals that was really popular way back in the day. Okay, so that's where that comes from. If you don't have me, then you probably don't even have this on your notes packet. I put these here so that my kids kind of laugh, right? Because in Physics C, we really put the C in Physics C, and the C stands for crying. So, I try to make them laugh at least a little bit. Okay. Um, we can induce EMF or current into a circuit using magnetism, and it's pretty cool. We cause what does that mean? It means that we cause, okay, a circuit to function or to have a current, okay, and behave like it has a battery, but it doesn't. Okay. Instead, we use magnetism. Okay, so you'll find that magnetism can actually be used to create currents and EMF to induce it into circuits where there is not a battery, right? And it's actually pretty interesting, but we look at it a little bit here, but that's something that you will really we really dive into when we circle back around to the calculus stuff. Okay. Um, there are a couple of situations in where a magnet can induce current in a wire loop, and then the situations where where what does it say? In which a magnet can induce current in a wire loop, and situations in where a wire cannot induce current. Okay, it should say magnet, right? There's situations where it can induce and where it cannot induce. A magnet can induce if the magnet is moving, okay, and coil is still, okay. I say coil, right? It's the same thing. A loop of wire is just a coil, right? The coil is moving, and magnet is still, okay. But in general, a generalized version of this is saying that there needs to be any relative motion between, okay, magnet and coil. Okay? A magnet cannot induce current if they're both standing still. Okay? Or if they move together. Okay? So if the magnet and coil are moving together or they stand still, in other words, no relative motion, then there cannot be any current induced, right? Because essentially, in one object's frame of reference, the other object is moving with. If they're moving together, right, in the coil's frame of reference, then the magnet is at rest because it's moving with it, right? And same thing. So from the frame of reference of one object to the other, there needs to be some motion. Okay. Um, a coil can induce current, okay, if if the current in the primary, okay, coil is in the process of charging, okay, but it cannot induce current if the current in primary, okay, coil is constant. Okay, so as long as the current in the primary coil is charging, or I think also discharging, then there can be induced current in the secondary coil. Okay, but if the current in the primary coil is constant, then it's not inducing current into the secondary coil. Right? You'll notice that the battery is connected to the primary coil, and then they're attached together by an iron bar, and then the secondary coil does not actually have a battery directly connected to it. These two wires are not, these two coils are not connected through anything other than the iron bar. Okay, and so a general conclusion that we can make about induced EMF, okay, just kind of tying everything back together, is that you need magnetic field to change in order to induce EMF, okay, and induce current. You can't have a current with zero EMF, right? Because if you think of Ohm's law, okay, you cannot have a current. You can't have if EMF is zero, then current is zero. Same thing the other way, right? EMF is equal to I times R. If you have zero current, then there's zero EMF, right? Okay. I think that's it. This is a really short section. Yeah, the next section is magnetic flux. Okay. All right. That's it for that one. See you next time.